So, hi guys, I think we are live now. I think we are live. Just give me 1 to 2 minutes and we will be starting with our topic, right? So, let's start, guys. So, now we will be started with our day one problem and today we will be going to solve some of the interesting problem related to the heap. And so we will be going to discuss first of all what is heap data structure, what is the motivation to learn heap, and like all the stuff, right, related to the each of the operations and their time complexities. And we will be learning to see how we can implement the heap, basically the priority queue data structure, with our STL container. And then we will be solving a bunch of problem related to heap. So let me just start with a like a little introduction about the heap data structure, and then we will be starting with uh, so let's firstly we will be going through like like what kind of operations and what is actually this heap data structure it is, right? So heap is nothing but a tree based data structure where we can store the element in a specific order, right? So actually the priority queue is the implementation of the heap, right? So let's firstly understand why we need heap, right? So what is heap? We already get familiar with. It's kind of a tree based data structure where the element will be storing in the specific order, right? Specific order, right? So actually uh, so let's understand this data structure with the help of example, right? So let's suppose there are n people standing in front of the bank queue, right, and this and people having specific age, right? So people, let's call n1 people, n2 people, and n3 people, right? So and they have their age, right? They have their different age, right? So let's say the n1 has 50-year-old and n2 has 25 23-year-old, and so on and so forth, right? That's it. And we need, so the bank employees need to serve the person who is older in age, right? Like n3 has 89-year-old, so bank wants to serve it first. So all the people having their own age, so we will be serving the people based on their priorities, right? So so what you, if suppose if you have given this problem, what you will do, right? So I have to serve and 3 first, right? So what you will be going to say, let's why not sort. So the first things that came to our mind, sort the, let's suppose this is array in descending order, right? Descending order, right? So what we will, what our actual array becomes, it becomes 89 and 53, 50 and 23, right? So so this becomes our actual array. And now what so let's analyze the time complexity. If you are going to use some kind of uh, sorting algorithm, let's say the merge sort and the cube sort, it definitely going to take log of n time, right? Log of n time, right? So let's suppose if we had a large number like 10 to the power 18 and 10 to the power 9, something like this, then we have to sort the entire array, right? So that's not a like a feasible solution. And let me give you one another example. Let's suppose there is a some kind of a test going on. Let's suppose it's a kind of a DSA test, and there will be like a 50,000 participants in that, right? So we need to give some kind of a prize, give prizes to top 10 or 100 students, right? So what we will be going to in that case, we will be just getting those students which scored higher marks, right? which which score higher marks. So that's the first thing. So here let's suppose if someone score 300 and someone score 500 and someone score 200, so we will be going to sort it, right? Like 500, 300 and 200, and then we will be going to give prizes to the n participants, right? So here if you see again, like we had used sorting, right? Sorting. So here is the problem slide. Like if you want to sort, just want to get 10 uh, 10 people out of 500 or 50,000, right? So you need to work on the all all the n values, right? So you will be going to sort. So what's like where to apply heap? Like if you see some kind of a this problem, let me just give you a trick where you can apply heap, right? So if you see some kind of this keyword, largest, smallest, right? Top something and k elements, like largest k element, smallest k element, then you will be definitely sure you can apply heap to this kind of a problem, right? This kind of a problem you can apply heap, right? So this is called the identification phase. So you will be seeing like if I got this kind of a problem, I will definitely apply heap there, right? So and this is kind of a motivation to learn heap, and we will be seeing what. So basically we have learned like it will be storing the data in the form of the tree itself. But if you see the actual implementation, let me just put it over here. If you see the actual implementation, right? So it will be based on array, right? based on array but but you have to visualize in the form of tree and binary tree, basically binary tree, right? So let's see first of all. So we had got the idea like it's kind of a priority queue based data structure, and we will be serving the element based on their priorities. So it has like the three main functions: the push and the top and the pop. So push basically adding one element to to the heap, right, and top will give the topmost element, right. So this is all about like a heap, right. So let me just go over here. And so we had learned is kind of a implementation of a priority queue, like, so it had uh, some kind of a heap order properties. So let's see with an example, like how this operation is actually implemented, right. So if you see, let's see. So where it is. Okay. It's not working. Working. Okay. Okay. So if you see here, uh, we had these elements, like what kind of operation that we can perform in heap, right. So let's go with this example, right. So here we had given our heap, and here is the actual implementation of the heap. So basically there are two kinds of a property that heap follows, right. And we can say that there are basically two kinds of a heaps, right. Two kinds of a heap. The first one will be the max heap, right, and the second one will be the min heap. So what that says actually, so what actually mean by that, right, we had two kinds of a heap. First is max heap and the second is min heap, right. Min heap. So what happened in the max heap, the element which had the highest priority will be served first, and same goes with the min heap, the element which has the lowest priority will serve first, right. So let's see in this example, right. So we had a array and we need to represent this this element in the heap format, right. So what happened, if we implement, if we visualize this array in the form of tree, so what happen in each node, right, in each node, right, what happen, the parent node is smaller than its children and it follows across all the trees, right. If you see any, this will happen in the min heap, right. So if you see here, right, uh, 2 is on the top and the left child of the 2 is 3 and the right child is 6, right, and this both 3 and 6 are greater than 2, right. And if you see at this level, right, 6 had 15, and 6 has as a left child as 15 and 6 has right child as 18, right. So these both are greater than the 6, and if you see across all the tree, these properties always follow across all the trees, right. So this is all about the min heap, right. If you talk about the max heap, what happen in max heap, max heap, uh, the root node is always greater than with their children's across all the nodes, right, across all the nodes. If you can see here, like 10 10 is greater than 5 and 2, right, 12 is greater than 1 and 6. So this is all about the representation of heap, right. And what happened, but in actually what happened, we will be implementing in the form of an array, right? So we will be actually implementing in the form of array. So what's why we are going to implement? So first we need to understand why we need to implement this in the form of array, right? So basically what happen is, like if you see, let's try to implement in the form of array, and then we will be seeing the like what will be the complexity and why we will be using our uh, why we'll be going with the array based implementation, right? So let's say there is a heap which has 2 as the root element, and then we have 4 and 6 here, right? And then we have, let's say, 10 and 12 here, and we have 70 or 80 here, 80 here, right? So this is our min heap, right? So min heap, right? So let's pause. So if, let me just give you some few properties of the heap, like the binary heap. So it will be going to a binary tree, right? Binary tree. And in binary tree it will be going to a complete binary tree, right? Complete binary tree. So what's happened in the complete binary tree, right? So all the levels would be completely filled, right? And the last level will be filled in left to right order. What that meant by is, like if you see, in this level we had at most one node, right? And in this level we have at most two nodes, right? And in this level we have at most four nodes. So what you can say, if I remove this element, right? If this element, does it a complete binary tree? No. To be a complete binary tree, all the levels should be filled except the last level, but the last level will be filled in left to right order, right? Left to right order. So it is goes here, and now we can say this is complete binary tree. Yes, it is a complete binary tree. So that's the complete binary tree property. And the another one is a heap order properties. Heap order property. Heap order property. Heap order property. So what's happening in the heap order properties? So if we are talking about the min heap, then what we had earlier said, the root element will be always lesser than both of its children, right? So this is a heap order property, and this remains same across all the tree, right? So it remains same across all the tree. And if you talk about the max heap, the reverse will go, the root element is always greater than with their children. So that's the heap, that's the heap order property, right? So let me erase everything. So we had learned about we had just learn about the different stuff related to the max heap, min heap, and we had just now we have to derive the complexities, right? What would be the complexity and why we are going to implement in the form of array, right? So let's suppose this is 3, 5, 11. Let's call it 11 and 12, right? So suppose we have to insert a new element, right? So we have to insert a new element, right? So what we will be doing is, let's suppose here is some x1 element and here is some x2 element, right? So we had total 1 and 2, 1 2 3 and 4, 7 elements in total, right? So let's suppose we have to insert a new element. So what we have to do to insert a new node, we always say it will be going to in the it will be inserted in the last node, right? the last place where we can insert new element, right? So to insert a new element, let's say we have to insert 70, right? We have to insert 70, right? So what we are, if we are going to implement in the form of tree, so what we need to traverse this, the root level, the zeroth level, the second level, the the last level, right? So to insert one element we need to traverse all the element, right? So it's kind of a, if we are to insert, suppose in total we have n elements, right? And we already inserted the n minus 1 elements, then we actually need to traverse through n minus 1 element, right? We need to traverse with n minus 1 element to insert only one element, right? So it's going to take much more time, right? If we do this stuff in the form of tree, right? So to insert we need to traverse all the level, so that's a very bad thing, right? So we need to optimize this, right? We need to optimize this, right? So it's kind of a order of n work we are doing at each element, right? To inserting an element. So then it's, then if we are spending over time, then it will be probably, then why should no we to insert a new element, we simply go with arrays, right? So what's the benefit of using heap, right? If we doing this in the over time, right? So that's the one thing here. So that's why we are not, if you are to delete an element, then you need to spend this amount of time, right? So that's why we are not using binary tree to implement this, right? So let me give you how you can do in the form of array. Let's number these elements, right, based on their indexes. Let's call it 1, 2, 3, 4, 5, 6 and 7, right? And let's try to insert here all the elements, okay? So 0, 1, 2, 3, 4, 5, 6, 7, 8, right? So 2 will go there, 3 will go there, 5 will go there, 11 will go there, 12 will go there, and let's call it 16 and 17, 16 and 17, and then we have at last 70, right? So in that case what we need to do is, like, we need to optimize this to insert a new element. We need to actually do this in log n time, right? Log n time, the height of the maximum height of the tree, right? We need to do in the log n. Let's say we need to insert 90, let's say we need to insert 0. So what we will be doing here is, we will be insert in the blank position of the tree. So like we did it here, so we will be inserting 0 at the empty space. So basically on the, if this is 8, this is 9, so we will be inserting in this 9th index, right? So if you see, right, what if we have to insert one element at last in array, so how much time it takes? It will simply take over time, right? So we need to just do this v dot push back, right? V dot push back, and we need to simply pass the data we have, right? So it will take just over time to insert 0. So here we had 0, not 90, not 90, we had 0, right? So it will take just order of one time, right? So now if you see, the size will be of the vector, or let's say the array, will be 10. So does 0 is inserted it their correct position? No, that's not the correct position to 0. It's violating the heap order property. So if you see here, like 11, so 11 has 70 which as a left child, which is greater than 11, and but it has 0 which is smaller than 11, so it's violating the heap order property. So we need to do some steps that will just do the insertion in order of log n time, right? So what you can see here, so let's me just give you a hint here. So what's the actual computation here is, so if you have to do in a log n step, so at least you need to traverse in this is a vertical order like this, like a ladder, right? So you can have to spend at least log n time, right? So if someone is, let's calculate some of the points here, like if 2 is at index 1, 2 is at index 1, so let me just write it here so it will be more clear. So I know it's the first time, and that's why even this is my first stream, so I will be doing something better in the future. So yeah, that's working fine. So let's suppose if 2 is there, right? 2 is at index, let's call it 2 is at index 1, right? So 2 is at index 1. So what would be the index of the left child, and what would be the index of their right child? So if you can see here, right, so the index of the left child would be nothing but 2, would be nothing but 2, and the right child will be at 3. So let me generalize in the form of I. So if a element at ith index, then the root will be present at 2i, and the left child and the right child will be present at 2i plus 1, right? So you can verify this property here. So if you see, like 2 is, this is the index of 3, which is 2, what would be the left child? It will be just 2 into I. 2 into I will be 2 into 2 will be 4, and 2i plus 1 will be 5. So that's the thing here. And similarly, if we need to find for an element, right, what will be the parent of this element? So let me do it here. So if we need to find the parent of some element, let's say I, here I is 9 and the parent will be 4. So you can, uh, if I is equal to 2i, the left child, then the parent will be nothing but I by 2, right? So if you see here, the 9 parent will be 9 by 2 will be nothing but 4, and the 8 parent will be nothing but 4. So what I am trying to say here, you can just catch out, grab the parent element, and then you need to just replace the element with the parent one, right? So you can check out here. So then the parent of the ninth index will be nothing but 4. So you will be seeing this 4, and you will be comparing 0 0 with 4. So it's 0 is actually smaller, so what you can do here, you just have to swap this element, right? So you had swap, and now your actual index will become 0, actually become 4, right? And what you need to check is, you need to check with its parent, so its parent will be nothing but 2, so you need to check at this index, and if this is also greater, you need to replace this, right? So you actually have to replace this, right? And yeah, that's the case here. We replaced with 2, and finally we will be going to replace with 2. So actual array will become 0, and 2 goes here, 5 remains here, right? And 3 goes here, and 12 remains here, and 70 came here, and 11 came here, right? So is this follows a mini property? Yeah, it follows a mini property, and we had uh, these elements are same here, right? So it follows a heap order property, right? So actually you are doing log n step here, right? So that's why the insertion in this case will take log n time, right? Log n time. So if you talk about, so this is all about the insertion part. So we had done with insertion part here. So let me just write it here. So the operation will be, so we had done with insertion, sorry, spelling mistake, insertion, and now we have to, so we had done the insertion in log n time, right? Log n time, log n time. Now we just need to do deletion, right? Deletion in log of n time. So let's see how we can do it. So let's suppose we had this element, let's say 2, 3, 5, and let's say 11 and 12, and let's say maybe 15 or 20. So what happened in the heap, right? Priority. So I already said you that the element will be fetched based on their priority, based on their, like, if they are having one, the minimum element or the maximum element, right? So what happened here is, let's suppose, so if we have to remove an element, it will always be the top element that we want to remove, right? So it may be the max heap or it may be the min heap, right? So what you can do here is, right, so you need to remove 2 from this place, right? So what's happen in deletion is, so what you have to do first is, so let's firstly represent in the form of array. So we had 2, 3, 5 and 11, we have 12, we have 15, and we had 20, right? We had 20 here, right? So let me just give the indexing here, and yeah. So what happen in insertion here is, oh sorry, the deletion part here is, so what we need to do here is just, so you can just not like directly delete the element, right? So if you think like this is the, this element you want to delete, right? So you need to like shift all the elements, right? Shift all the element. If you, let's suppose you simply delete this element, so you need to shift all the element, and that will going to take order of n time, right? Order of n time, right? So this is a very bad approach here. We have to optimize this. So we just have to come up with some kind of a log n solution. Here is, so what we will be doing here is, we are going to replace this element with the last element, right? So if you have to find this element, so it's become simply array of one index, and if you want to find it the last index, you can find it in even one time. And then what you have to do, you have to just swap this element, right? So 20 comes here and 2 goes from here. Oh, sorry. Oh, so 2 goes here, so I actually replace this 2, right? So I actually replace this 2 with 20, right? And then what you have to do, you have to do one operation that we call a heapify operation. So heapify operation, this is actually the main part here, right? That's the reason the complexity bring down to the order of log n, right? I will be just prove within a minute here. So if you see, right, so we had just replaced. So what's the hippify property does it? Let's suppose you had like 5 here and 3 here and 0 here. So what the hippify operation does it actually place the element in their correct position. What that actually means, it's actually find the minimum element, right? So what the, if assume that, let's we create a pointer, let's call it min index. So actually this is our min index. So what's hippify does it's compare with the left child, right? If that is smaller, then this will our become min index, right? So this will become our min index, and then it is compare with this right child, right? If the right child is smaller, then it will be becoming mean index over here, right? So actually it is finding out which is the smallest element between these three elements, right? So once we find the minimum element, we just replace with the root one, right? So what happened is it's became 0 and it's become 5 here, right? So we just simply do this hippify operation, right? So in that case also, right, so we will be finding this element, so this become the our minimum sorry sorry yeah. So actually before going to this simplify operation, what we will actually do, we will actually just leave out this node and we will remove this node from here, and then we will just simply do an simplify operation, right? So if you see, yeah, yeah, so so it will be comparing from this element, right? This element, and we will be finding out the minimum element and replace the minimum element, right? So 3 goes here, 21 goes here, right? And again we heapify operation perform at this level is, we will find the minimum element and 11 goes here, right? And actually if you see 3 11 5, the resultant heap 21 and here 12 and here 15. So this is actually the correct heap we got, the correct minimum heap. So we are just performing this operation. I had performed, I went to this node and then went to this node, right? So it's like a top down traversal, right? Top down traversal level wise, right? So we will be doing one operation at each level, right? So if we had logan level, so we had performed logan operations, right? So that's boiled down to the fact the remove operation takes order of logan time, right? And if we the get operation to find out which is the topmost element, it's going to be just simply oven operation, right? So that's all about the concept here. So uh, removing to remove one element, what we have to do is we have to replace the first element, replace first element with last one, right? Then we simply remove the node for the element, right? And then we will perform heapify operation, right? So that's all about the concept here, right? So that's why in the blog they have mentioned that, so push operation will take log n time, and pop operation also takes log n time, and the topmost element will do in order of 110. So I know it seems boring, and now we will be jumping into the coding part, right? So it's, you had a great idea from here, right? So what's the actually the benefit of using it? So we are done with this part, right? So we are done with this part where, so I already told you where you can apply if this is the whole example here, right? So in most of the problem, like you have been given this kind of a keywords, or the problem where you need to actually sort all the so basically you are saying like I will be sorting all the parts and all the array, right? It may be array, linked list, anything, right? And it could be a hash table we will be seeing in our next problems, right? Right. So you will be getting a feeling like I should sort whole array, right? But the problem boils down to the fact, right? You don't need to solve whole array, right? So that's, you can came across this kind of a problem in your interviews, right? So it's a very important data structure, right? It's help you in your problem solving skills, right? Different kind of a problem. I already told you this kind of a scenario, like the coding contest or something going on, right? The banking queue where you need to get prioritize your task, right? Based on different kind of keys, right? So that's the whole scenario. And one of the like major of the times, if you can see this kind of a thing, like the largest, finding the largest kth element, maybe anything like smallest one, right? So you can pretty sure you can apply a heap data structure, but your first priority will be to give a brute force kind of a solution, and then just jump into like thinking why the brute force will not help us, right? And then you will be going to simply jump on the heap part, right? You can think of like what should I apply, the max heap and the mini heap, right? You can think, so you have to think out loud there, right? So we done with like where you can apply the heap data structure. We had learned the motivation, like motivation real example, right? So where you can apply it, right? So we already done a dry run for the complexity part, and I already showed you in a diagrammatical way how the complexity being computed there, and so how you can visualize the heap in the form of the tree and actually implement in the form of arrays, right? So we are done with this part, so we are left with the container part. Before going to the container part, let's see the implementation of the heap, right? See the implementation of the heap before going to the uh, containerized part, right? So actually, so it's STL really helps us to like figure out ex- uh, figure out the stuff, right? So we will be seeing this all. So let's start with the implementation part. So let me just open this implementation. Where is implementation? Here, right? So yeah, that's the implementation. uh, so what I have told you, right? So just ignore this stuff. So we will be creating an array, right? So we will be creating an array to store the elements, right, in the form of a heap. So I just created an array, right, in the form of heap, and in the form of array, like to insert the new elements. And what we had is like we can implement mini heap and max heap. Let's try to just forget about the max heap part here and just focus on the mini heap, right? So just ignore this stuff right now. Just ignore this stuff. We had just created a vector, right? And now what we have to do here is like, so already I already told you, like, let me explain it here, right? So it will be more clear. So so first we need to like create an array, right? So what we have done in the example, we have stored all the elements in the form of array. Like, so we had this kind of a, actually we had this kind of a thing here, right? 2 5, and here we got something called, let's say, 15 14 15, and then we got something like 40 40 and then 50, right? So let's try to insert this in the form of array. So 2 3 5 14 15 14 14, right? So this is a mini, right? And let me just give you the indexing of this element: 5 6 7, right? So always, right, so for the computation purpose, always let's uh, don't like block the zeroth index, right? So it will be easier for us. So I just block the zeroth index, right? So yeah, so we had created an array and we block the zeroth index, right, from there, right? So I just do it here, and now what we need to do is we need to insert one more element. Let's suppose we need to insert let's suppose we need to insert our data will be like 100. No, not 100. Let's say we need to insert 1, right? So the correct position will be at this, right? And we need to insert 100. So what we will be, oh sorry, the 1. So what we will be going to create, we will be just uh, looking for the first place where we can insert. So uh, hope you remember that the heap will be satisfy the complete binary tree property, right? And also the heap order property should be maintained, right? Should be maintained, right? So what we had done is we had inserted the element at the last. So we need to insert this element 1 at the 8th index, right? So just focus on the example part and it really helps you to understand. And then what we have done is, so we had inserted 8 here, and at the at the last, right? So it takes over time, right? So if you see what is the size of our array, right? Right now what is the size of our array? Right now the size is 9, right? Right now the size is 9. So, and we need to compare 1 with 14, right? And we need to figure out at which index 14 is, right? So if you compute the actual index of the element is 8, right? So index would be 8, right? So how we will get 8? So we know the size is right now the 9, and the last index will be nothing but size minus 1, right? Size minus 1. So we will got the last index from it. And if you need to compute the parent, so the parent will be at index divided by 2, right? So I already tell you why it is at the, I just give you the computation why it is at the index, particular index by 2, right? So we need to compare these elements. Once we got this element, so we need to compare if we at index, if 1 is smaller than 6 or 40, right? If it is smaller, then we will swap it, right? So in that case, so I will tell you why I wrote this condition. It's just to uh, get the topmost element, right? If it is greater, then we will be do swapping, right? If it is already something like the 0, then we don't have to do swapping, right? So that's why I wrote this condition in here. So if you think, right, so we need to just swap it, right? I need to just swap it with 14. So we just swap it, right? And now our actual parent will become parent divided. So then this parent will be at, we have just we have something 14 two times, right? So we just ignore it. Yeah, we can have 14 two times. We can have the same element. Just ignore, yeah, we are right. So what we need to do here is we are done with this, and we actually got our parent at index. Our parent index is nothing but 4, right? Our parent index is at 4, and now we need to compare with its parents, right? So its parent will be nothing but 4 divided by 2. At 2 index we had 3, which is also smaller. Then again we will be swapping this element with 3, right? And again at 2 we need to just swap it, right? So we are done with swapping. So we had done with the swapping part, and we actually got 1 at its correct position, right? So we are done with the swapping, and we actually got the 1 with. So at last the 1 will be at its correct position. So that's the whole push operations that I have performed with you, right? So the comparison logic will goes like 1 is smaller than 14, right? So here is the actually the comparator is, if it is a min heap and 1 is smaller than the 14, so it will be returning true in case of a min heap, right? So we will be doing this swapping. So this is all about the swapping part. Oh, the push operation. Now we will be focusing on the pop operation. So what I have told you earlier, in pop operation we will be replacing, so in pop operation, right? So I have told you, you have to remove the first element, right? The topmost element. So you need to replace with the last element, with the last element, right? So let me just write it in a correct form here, like 1 2 5 3, it's 3 15 40 40 and 14 and 14 and 14, right? So if you need to remove this element, so you need to just replace with the last element, right? So 14 will goes here and 1 will goes here, right? And you just need, so you had 9 elements, then you can just simply decrease your size by 1, right? So it will become 8, right? It will become 8, and this element will be uh, uh, automatically get removed, right? So you just remove this element, and then you need to perform the pp5 operations, right? So I had done the same step here. So you got the element, you just decreases the indexes of the, and then you have done the swapping, and then you have removed the last element, and then you have perform pp5. So what does the Heapify operation so the 14, so it will just kind of do kind of log n steps to get its correct position, right? So I just said you, so you need to compute the left index and the right index. So you just created your left index and the right index, and you just mark the 14 as a min index, right? So you need to perform the heapify at this index, right? At the first index. So it's always going to be the first index where you need to perform the heapify in case of a pop operation. So you just need to get this element, right? And then you just need to get the heapify. So yeah, so here you will get the the last index, right? So what will be your last index, right? So yeah, this will tell you where the heap is going to end, right? So you will check, right? You will check v dot left, so which is smaller, right? If v, so v dot left is 2 smaller than 14, yeah, it's smaller than 14, then mark min index as a left, right? And then you will compare if you had if you are within a range of last index, yes, I had range. Is this smaller? No, it is no smaller. So actually you got your min index, right? So here you got your min index at 2. So what you will be doing, this is actually not the in the correct position, this are the not same, and then what you have to do, you just need to swap those elements, right? Then you need to swap those elements, and you need to perform heapify recursively on this part, right? On this part, so it's like 14 goes here and 2 came here, right? And again you need to do heapify here. So it's 14 goes here and 3 goes here, right? 3 goes here, right? And at this step, right, at this step, just focus on this part. At this step you go to your index, it will be 1 2 3 1 2 3 4 4. You go simplify at 4 index, right? So you compute left will be 4 into 2 8, right? So left will be nothing but 8, and right will be nothing but 10, no, 9, right? So you will be seeing, right? So what is our last the last index, right? So our last index is nothing but 7, right? 7, right? And here this condition doesn't true, so left, so we had no more another nodes, right? No more another nodes, right? So no more other nodes, you can not perform this operation, and you can even don't perform this operation, right? And even this is like a same, so it will be, so min index and index will be same, right? So here it will be same, so this operation, and then exit out from the loop, right? So here we had performed login steps to perform this kind of operation. So that's the another part here. And this is to check if that is empty, and it will be just returning out the element, and this is just printing all the elements, right? So this is the whole implementation. of the heap data structure, right? And to just simulate the process for the maxi property, so you can make a boolean variable min heap. So it will be tell you if this is a min heap or max heap, and the things will remain same for the both heap, right? So here you get the clear idea about the max or the min and the max heap. Okay, so you are done with the most challenging part here, and now let's, so we had done with this part, and let me tell you, you don't need to like, yeah, for the coding interview, yeah, they can ask the like the low level implementation of the data structure, how the data structure is implemented. So you just have to like elaborate, yeah, we can visualize in the form of a tree, but the actual implementation boiled down to the fact for array, right? So yeah, but yeah, if you need so solving some problems on competitive programming side, right, then you can use the stl container for the priority queue, and yeah, it will be super easy for your task. So let me just write down some of the like boilerplate for this part. And so actually it is presented on itself the queue library, so you just need to like just write it here. So I still, so it's actually implemented in in the form of the library. So you just had to like hash include uh, queue, right? So you just need to include the queue library, and then you can create your priority queues like hash include vector. So you just need to include queue, right? Hash include queue, and you can create your priority queue by this, right? So by default this will create you max heap, right? But if you want to create a min heap, so what you need to do, you just need to pass this parameter, this competitor here, right? So we need to pass this greater than competitor here. So sheets like vector right, background, and you can search on the internet, right? Greater than competitor to create meaning. And let me just give you the functions. So one will be the push function, right? So and another will be the pop function, and the third one will be the top function, and the fourth one will be the size function, and the fifth one will be the empty function, right? For basically to checking whether empty or not, right? So it will be helping you in like traversing the arrays, traversing the arrays, right? So yeah, that's the like implementation of the priority queues, right? If you want to see a live hands-on on the priority queue, so I will be coding for you, right? It's not a big deal, right? So let's call it STL. So I actually implemented. Let me write it again for your understanding. It's become a very easy part. So you just need to like include this stuff, like so. So you had this library. So what you need to do? Let's suppose we need to implement max heap, right? Max heap to store the elements. So what you can do? You just need to create a priority queue, like let's call it pq, and you just need to insert element, let's say 50, and pq dot push 100 and let's pick the road push 20, right? So I had inserted this element, right? Right, and if you just print out this, like what should be the size of the array. Oh, so for the priority queue, right? For the priority queue. So let me see if it is working on it. Not finished with the compilation. So I think it's not working. Don't know why. So let me just do a check here. Just print out one statement to check if it is working or not. Hello, hello, and so yeah, that's working. It's working here. So just comment out the net once more time. So yeah, that's printing the element, right? That is actually printing the element, right? So if you want to just see, like display all the element, right? Let's traverse all the elements. So what you have to do, you just need to write a while loop, and while our priority of queue is not empty, give me the topmost element, right? Give me the topmost element, pq.top, right? And give me like a space, maybe ender here, and just pop out the element, right? Pop out the element. So let's see what it will give us. So yeah, we are getting the element with the priorities, right? And if you want to see how we can implement like main here, so you just need to pass vector here, right? And you need to pass the, so it's actually intuitive compatible, right? So you need to just pass it here and see. So yeah, you will be getting the element in reverse priority, right? The mini priority, right? So yeah, so that's the actual implementation of using priority queue, right? In the programs we will be mostly using this STL container, right? But if the interviewer asks you to write the whole, like it will not going to ask you, right? So it will be just a 25 or 45-minute interview. So it will be just not ask you, it will be going to see your approach, right? So yeah, so we had done with this part, and now we will be like, we are done with the implementation. We learn about how to implement in S3 container, and let's now jump the real part, the coding part of the different programs, right? So you will be getting a more clear idea where to apply heap or not. So I will be explaining the old stuff, right? I will be telling you firstly the think out loud about the brute force solution, and then jump into the like the optimal solution, right? So these are kind of a basic problems, right? I wrote it down here, right? This is a basic problems where you can like apply it. So we will be learning firstly this part, and the flow will be, I will be telling you the problem statement. So let me just write the flow. So I will be telling you the problem statement, problem statement, and then we will be going to see what's the our input and output format. So what will be our input and output, and then we will be going for a brute force solution, right? Then we will be going for a brute force solution, then we will be optimizing it, right? Then we will be going to optimize it after analyzing the complexity. After complexity analysis, right, we will be optimizing this solution, and then we will be going to, can we apply min or max it, right? And then again we will be dry run, right? dry dry run. So that's the, like, the whole flow will be goes. So without, so here starts with the problem part, right? So so what you have given is, let's jump into these sites and just jump into, let me just see. Just open leetcode.com. So let's start with this problem. Uh, let's start with this problem. Let's try to understand this problem, and then we will be moving forward. So what the problem says is, given an array, you have given an integer array and an integer k values, and you need to return the kth largest element, right? You need to return the largest element. So you had given this array and you had given this k value, so you need to return the kth largest element and not the kth distinct element. Yeah, so you need to return the kth largest element, right? So let me just copy it here and then jump into this part, right? So already, yeah, I already mentioned this problem, right? So you had given this array, right? So your actual array will be this. So if, right, so let me just zoom it out a little more so you can see properly, right? So you had given this array, and you just need to, what you have to do is, so you need to find the kth largest element, right? So what would be the, if you think what should be the like the first largest element, right? So what is the first largest, so obviously in this, if you see, the largest will be 6 and the second largest will be fifth, right? The fifth element, not the fifth element, the fifth one. And yeah, so that's is the largest element, right? So you need to return this element if case value is 2, right? So what should the first things that comes across your mind, right? So you can say, yeah, I can do, I will like sort the array in the descending order, right? And then I will simply grab out, if you think this is a zero based indexing, so the correct answer would be nothing but at actually the k, it will be k minus 1, right? If it is 2, then it will be present in 2 minus 1, nothing but 1, right? So this is our answer. So you had set this solution to the interviewer. So yeah, that's kind of a pretty easy problem if you think in terms of like just the problem, right? So what makes these problems more interesting is, right? So you will be saying I will be doing, so what should be the complexity? So it should be you are just doing a sorting, so it will be taking like n log n time to sort the arrays, and then you will be just doing an O1 operation, like constant operation, to fetch out, manipulate this, access that element, right? The kth element, it will be at, if the zero based indexing, it will be at k minus 1 for sure, right? So then, right, so you can, and what would be the complexity? So we are not using any other, it will be open, right? So yeah, so you had done this. So the next question, the interviewer will be asking you, could you just optimize it, right? Can you think of some another better solution, right? So analog, right? So uh, the second things that came to your mind, right? You need to just get the second element, right? Second element, right? It's kind of a, like if you have a 1000 2000 student, you need to get the top student, right? Top student. So actually you don't require all the elements, you just need to the particular element, the kth element, right? So in that case, what you can do here is, like, so you had this element, so you can think of, right, you will be saying, okay, then what I will be doing is, so what happen in n log n solution, let's try to figure out how we can optimize from n log n, right? So I will be not straightforward to use heap, just think out loud, right? So what happen, you are inserting n elements, right? N elements in a box, right? And then it will take log n steps to sort those elements. So you need to just find, your, like, the main observation will be here is, you just need to, like, you not need to put n elements, right? Just you need to find out, you you really caring about some k elements, right? Not n elements, right? So you are caring about, so you can ignore n elements, but you mostly care about like the top k elements, right? So instead of inserting n elements, what you can do, you can insert only k elements, right? So let's suppose, let's try to understand. The coding part is like pretty easy, and like the, like, interviewer will be like more much to understand what you actually thinking, right? Why you are actually going for, yeah, for sure we are doing a live stream with a heap, and then probably we will be going to use heap, right, to optimize the solution. So but you need to think out something, right? Like why you are using heap, right? Just need, you cannot just go with like, yeah, I will be using heap, and you will be just set. So why you are, so you are really care about the k elements, not the n elements, right? So what you can do here is, so suppose in a box we will be inserting k elements, only k elements, right? K elements, it may be top or not from the n elements. So if you had n elements, right, so you are really care about only k elements, right? So you are only care about k elements. Then what your thought process will be, like, I will insert some element in a box, right? And in that box I will be maintaining only k elements, right? If something is kind of a, like, something larger element came while traversing some kind of arrays, and I think in my box some, uh, like some kind of a smaller element is present, then I just throw out the smaller element and then insert the largest element in the bucket, right? So I will be maintaining only k elements, right? I will be maintaining only k elements because the problem statements focus on only k elements, right? So yeah, so 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 you will be thinking like what I can use it, right? So if I maintain a box in which I insert first k elements, let's say k is 2, I insert a 2 here, right? So then I came across with 1, right? So my job is to, if I see like 1 is greater any of the element, right, any of the element, then I will be inserting. If it is actually smaller, all the k elements that are present in bucket, then it will be not our like the possible answer, right? It will be not our possible answer, right? Then again what you can do here is like you just ignore one, right? Then you came across 5, so your job is to maintain k largest element, right? So you will be throwing out like I will be remove this 2 and put 5 here, right? So you are maintaining this element, right, this element. And again you came across 6, you find this smaller element which is 2 and you will replace this with 6. Then you can came across 4, 4, so 4, so there is no element that is smaller than 4 is greater than any of the elements, so you will be not considered, you just ignore it. So I just ignore the element. Then so here comes like what to use. So I had said earlier, so we are done with like the problem statement, input output, brute force, right? And we are optimizing, thinking out loudly about the solution, right? And then now what we did is we actually find what kind of a heap does these problems, we can use some kind of a heap, right? So actually if you see, right, if you inserted 2 or 3 at the initial stage, right, and then you picking out the minimum element, right, and then replacing it with the largest element, right? If you pick up this element and then replace with 5, now the minimum becomes 3, so you are removing just the minimum element at the top. And what kind of a heap we can use to maintain, to get out the minimum element, like a uh, logarithmic type, log n stuff, log or log n or log k, right? So at most heap you have k elements, and min heaps help you to get that element, right? So you are just, in worst case what will be happen, you will be inserting if this are in suppose like descending order, right? Oh sorry, the ascending order. So you will be just, let's put this, right? So you will insert this element, you will be every time for every element you have to pop it out, right, and insert the new element, right? And then you have to pop it out and then insert the, so you are just, and the pop and the push operation takes log and time, right? It takes log and time, right, when we are an element in the heap. But now we had only with k elements, we had only with k elements, so it will take log k time. And for how many number of times we are going to do, we are going to do with all the elements. And how many elements we had, we had only n elements. So the overall complexity boiled down to the fact is order of log k, right? So that's the uh, issue. That's the solution here. Sorry. Um, so let me just write the code for the same. So it is pretty easy. So what we had discussed, we had to maintain a priority queue, right? So we will just write the code for the same, right? So I will create a priority queue. So I already told you how to create a priority queue. And here I need to pass this and greater int comparator, and here it will be pq, right? And we need to insert first k elements, insert first k elements in here, okay. heap. And so what you can do here is you will write a loop for k if it is to sufficient, and you just insert array of I, sorry, now so bad. So you just insert k element. Now what you have to do is for the rest of the elements, right? For the rest of the elements, int I will be at k. So you have done with 0 and 1, two elements you have already inserted. Now k2 numbers of size. So you need to traverse the rest of the elements and you need to check if pq.top, so it will give you the top element. If it is lesser than this I element, right? I element. If this condition happens, what you need to do? You need to pop out, right? Pop out the element and pop out the element. Just you need to pop out the element and just need to insert other element, right? Other element. So yeah, you just popped out that element and pop out the top element and push out the current element array of height, right? So yeah, that's the case here. You are popping out and at last you are left with yeah, the smallest element, the kth element. We get the top, and then you just need to simply, after this, you need to just need to give the top element, right? So pq.top will give you the result. So yeah, that's it. Let's try to submit on record. So I made it. Let me just figure it out. This is working on it. So yeah, array. Oh sorry, here not array. Here is will be number. Number. So yeah, that's the correct answer. Let's try to submit it, and I will show you one thing. So yeah, that's it's take a like if yeah. So that's the correct answer. We had solved this problem in order of log and case time. So right guys, so we already solved one problem, and now I will be discussing within just 5 minutes the another problem, and you can solve it by your own, right? You can solve it by your own, so it's like your task, right? And so what you had given is you had given uh, so sort a k sorted array. So let me just try to explain what's the problem statement in this. So yeah, that's the problem set. So what you have given is you have given an array which is partially sorted. What does mean it by the partially sorted array? So it means that the each element is not actually the each element is not at their correct position. It to be it like for an element to be in at correct position, it is actually mentioned that it is its correct position cannot be more than k, right? Cannot be more than k. So what is that means? If you see this array, right, so what should be the one it as correct position, right, to be sorted. The fourth correct position will be not this, so 2 will goes here, 3 will goes here, and 4 is goes here, right? So if you see this distance, the correct position distance and the current position, it is not more than 2. So 1 and 2, not more than 2. And this implies for the all the elements. This implies for all the elements, right? So this is a partially sorted array and you need to sort it fully, right? And here you have given is n scale. So one things that that comes across your mind, let's try to sort it whole, right? But that's not a like a big issue, right? You can sort it in n log, but the problem more focused on the kth, right? The like the longest distance will be not more than k. So it's like you are not focusing on the problem statement, right? So problem statement just says that every element at most like partially sorted and at most like k steps farther from the actual uh, position, right? So 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 what you can think of, right, what you can think of, you can say, right? So like if you need to figure out what should be the correct position of one, right? One is actually it says correct position. So let's think of four, like four let's think of what would be the element that will be inserted in the second position, right? Second position. So it's basically might be the 4 is the correct position for this element, right? For this index might be the 5, might be the 2, but if you see actually the 2 is the correct position for this element. So you are pretty sure from this like 3 elements only one element. See, like you had like the choice, right? You are pretty sure from these three elements, uh, one element will have being placed to this position, like 2 is going to place at this position, right? You are pretty sure. And for the case of the this index, you are pretty sure the you sorted this part and you are pretty sure then the correct position will be any of the 3 element from this, right? So you what you can do, you can just simply for this element, right, for this element you can choose from, you can put this 3 element in a heap, meaning, right, you are finding, you are assigning the integers values, right, in the the correct positions, right? So you can choose any, you can insert these 3 elements, basically the k plus 1 element in a heap, and you will get the smallest element out of it, right? So once you are placed one element, you will be inserting one more elements, right, one more element from here, right, and you will be inserting this. So this is how you can sort all the array. You are just inserting k plus 1 elements, so it will be kind of, and you are doing for the n elements, and the complexity boils down to n log k plus 1 only, right? So that's the, we have created a like a mini heap, and like we have pushed the elements, and for we are maintaining, we are just like we are used k plus 1 elements, and then we are just popping out and and pushing the next element, right? So that's, and all the remaining, right, all the, if the whole the list is over, we will be inserting remaining elements in the queue. So yeah, that's the whole part. So we had solved two problems, guys, and it's the first stream, and we will be looking forward to solve more problems onwards, right? So just give a check here, and we are uh, yeah, so we are done. Bye bye, and see you in another session. So I will be ending this